I'd like everyone to give a warm welcome to Blake Hannaford, a professor of electrical and computer engineering at the University of Washington. Blake's widely recognized leader in surgical robotics, surgical skill modeling, and haptic interfaces. Professor Hannaford's received his BS degree in engineering and applied science at Yale University and his MS and PhD in electrical and computer engineering at UC Berkeley. He has a storied career working at initially JPL's Man-Machine Systems Group. More recently, had a stint at Verily Life Sciences, which is formerly Google Life Sciences. He's throughout this time, he's been mostly at University of Washington's Electrical and Computer Engineering Department. And I think more recently, he's developed the Master's of Science and Technology Innovation Robotics degree option at the GIX program in Bellevue, Washington. I'm curious to hear about that because we're thinking about doing something lesser but similar here. His notable honors include the National Science Foundation's Presidential Young Investigator Award, Early Career Achievement Award from the IEEE Engineering in Medicine and Biology Society, and was named an IEEE Fellow in 2005. So the title of his talk is Remote Surgery Over the Internet, What Could Go Wrong? And I imagine many things could go wrong. I'm very interested in hearing about that. I ask that if you have any questions, you type them into the chat so that we can kind of aggregate them and kind of collect things common together. Before we talk, I also want to mention, I will see everyone again in October. So this will be the last seminar for the academic year. And with that, I'll pass the baton over to Blake.
Great. Thank you so much, Mike, for that introduction. And it's really fun to be here. I have a long. I'm a big Wisconsin fan, and my family still has a cabin in the far north, up near Lake Superior on the Brule River, which unfortunately I haven't traveled to in a couple of years. But I just, have the heartstrings pulled back there, and so I have a lot of ties with Wisconsin, and really happy to be here. So I'll share screen, but a host has disabled that. So Mike, if you can enable me to share screen, you guys don't have to look at my face for the next 45 minutes. Let's try it again. Yeah, here we go. And I can do that full screen on the other desktop. Everybody see my screen okay? Okay, great. So yeah, we're the other UW out in Seattle. The university rebranded with a huge W, and I thought that was really provincial and stupid, because what about Wyoming and Wisconsin and Winnipeg or whatever? And it just isn't a global brand. It's a Pacific Northwest brand. So I thought it was, but maybe it raised a bunch of money. Anyway, and you can see the date here, which I just realized I forgot to change. So I really apologize for confusing the time zones and booking something super important on that day on March 4th, 2022. So, but here I am finally. So that's what it was like this winter, and now it's spring, but it's not as nice a spring as we would have liked. But that's our building for electrical and computer engineering. So yeah, I just want to thank and call out really I'm going to be talking about work going back quite a ways, and that means lots and lots of people. And we have the medical collaborators, which just have been, super critical in helping us, make sure that what we do is medically relevant. And it certainly takes a lot of effort, especially initially, on both sides. You just have to match the effort to learn each other's language and build a, really meaningful collaboration, which I think we've done, and I'm proud of. And then lots of key students in the upper right here, and many, many more, including, and the new ones actually are not really here yet, not really represented here. So I need to update this, but I will try to call people out. And then Jacob Rosen, Howard Chiswick, Gaetano, the late Gaetano Borriello, and then great colleagues at other places like at Hopkins, Stanford, Berkeley, and many others. And I'm actually zooming on Jacob Rosen, who's now a professor of mechanical at UCLA, because you're going to see a lot of hardware gadgets, and this is really the genius behind our hardware, um, and lots of our control and sensing too. But there's no way that the hardware that you're going to see would come out of my brain. And this is Jacob has a whole other research area on exoskeletons, and that's one of his cooler creations, in my opinion. So it took me like 20 years in surgical robotics before I found these old things, which are unbelievable. This is the 1920s, and somebody figured out it would be really great to have remote surgery using the technology of radio and television. And this clearly lays out, the key ideas in remote surgery with these lightning bolt radio waves and the ability a surgeon console with haptic feedback, and it's just unbelievable that somebody could think of this in the 1920s and then update it in the 1950s with a sort of more current looking TV camera and arms and so forth. And so this is just I just love this because it shows you that science fiction is sometimes takes a really long time to arrive. And this is Hugo Gernsback, who is the guy who developed this as a young sci-fi writer, and he also developed the head-mounted display. So what a visionary! He apparently he was the editor of a sci-fi magazine, and he was kind of mean to the writers, but still, wow. And so then flash forward, you have 2001, Dr. Marisco from Strasbourg did a special thing where he did an actual human patient transatlantic with the collaboration of France Telecom and a kind of old school direct hardwired link. Not exactly hardwired, but the ISDN was this sort of clunky digital version of dial-up back in the day, and he had to be down in southern Manhattan because that was like really close to where the transatlantic cable came out of the ocean, and that was to minimize latency. And of course, this happened about 4 days prior to 9/11, so it had a very brief media splash, and then nobody cared, nobody read about it anymore for obvious reasons. But it's a major milestone, and that old technology comes from the Manhattan Project of all things, where they developed this guy Ray Gertz developed these manipulators because it was impossible to be far enough away with tongs to handle the radioisotopes in the Manhattan Project. And so this sort of ultimate military motivation, kind of led to, at least conceptually, the technology that we're using for remote surgery or even local robotic surgery. And this is sort of rare footage from those days. And it's still in wide use. So I was lucky to go on a sort of federal government research visit to the Hannaford nuclear waste facility with a panel of, like, that's Red Whitaker dressed in red, the CMU field robotics legend. And we were there looking at, how DOE could upgrade robotics into waste processing, which is still done today. This is a not only is this still in use, but this is a brand new installation at the Hannaford site, or let's say 5-year-old installation. So then, of course, commercially and going mainstream into medicine was the Da Vinci surgical robot by Intuitive Surgical, which uh, gives is used literally millions of times per year worldwide, and is now a major paradigm in surgery. The New York Times just published a article in the last few days on a meta-analysis of surgical robotics studies, and they said that it showed that it doesn't make a difference. But what they did show was small benefits in about 6 categories or 6 metrics, where the surgical robot surgery was actually better by a small amount in 6 different categories. And to me, that's a huge win, because you really want to multiply all those figures of merit together. And if you're 10% better in 6 categories, that's like being 60% better overall. So I thought they had sort of a pessimistic view of strong data, and for sure it did not show there was anything worse about surgical robotics. Yes, there's a higher cost. Okay. Oh yeah, this is very important. So historically, there's been bad terminology used in this field, and you can find about 50 publications by me using this bad technology in the past, but I don't do it anymore, and I want to call it out. So the terms master and slave have been used a lot to describe the mechanism held by the operator and doing the remote work, respectively. And there's a huge cultural bad weighting function applied to those terms for obvious reasons. And I used to have various rationalizations like, well, there's nothing wrong with a robot being a slave. Okay. However, the real way to think about it, the way my thinking has evolved, and I strongly advocate, is it doesn't matter what I think. It matters that people are offended by this terminology. And that's all I need to pay attention to, really. And if that's the case, let's change it. So there is no, there are people in the IEEE, telerobotics or technical committee who are trying to standardize this, and that'll take a while, but I'm using leader and follower to replace those terms. So, really a long time ago now, an amazingly long time ago, we built this robot for this endoscopic surgery robot because we wanted a research platform. And the Da Vinci was just coming out, and it was $2 million, and there was no way to, even if, as some labs did, like you get a wealthy donor to give you a Da Vinci for research, which happened in a few places, it's still a closed up system, and you can't get in there and change the control system or do, or even at that point, you couldn't even get data out of it. So we felt the need to enable research in this area with a new device. There were a couple other design goals. This is the original team. And like Diana is a key engineer at Intuitive for the last many years. And Denny Trimble designed many of these mechanical parts, and he's like the lead structural engineer at Blue Origin. And all these people have gone on to bigger and better things, except me. Actually, that's a good point to bring up. Yeah, because I have kind of moved on. I just as a sort of disclosure, I've taken a leave from UW, and I'm now full-time at Meta Reality Labs Research in Redmond, Washington, and having a great time kind of diving in to a very largely scaled haptic interfaces research activity, which I can't talk about today, but hopefully sometime can come back and talk about. So anyway, we designed, this very interesting spherical mechanism concept to, again, respect the insertion point in laparoscopic surgery, and we mocked it up with just a passive mock-up because we know that it constrains the surgeon. So we actually did pig surgery using this to make sure that it wouldn't block any necessary moves. This has a limited workspace, limited range of motion. We thought it was good enough. Was it good enough? Yes, it was good enough. So then we were able to adjust the link angles in this passive spherical mechanism until we got good, you could say, ergonomics and functionality. So then we engaged in field projects, and this is sort of slightly diverging away from pure research. Although we had experiments that we designed to run in these situations. There was that was sort of a not the driving function of these projects. These were sponsored by the military and by NASA, respectively, and I'll go into them a little more. But we did that, and what I guess I should mention that besides this level of animal verification, we did an animal verification with the actual eventual robot too, which went pretty well. So these are technology experiments rather than pure research. And the first one was called, don't ask me what this acronym stands for anymore. It's long out of my mind. I didn't make it up either. The PI was Dr. Broderick from the University of Cincinnati. He became a Army robotics program manager, eventually medical robotics. Our lab, AeroVironment, a drone company. I'm sorry, I can't remember what High Vision's role was. Maybe some cameras. And this is, again, quite a while ago, but a very memorable one. The goal was to demonstrate field operation of a surgical robot because our original sponsors were the Army for combat casualty care near the point of injury. And that's a goal that the military is kind of indecisive about in a good way. They push it for a few years, and then they decide, no, the main thing is stabilize the casualty and get them off to Germany as fast as possible for hospital care by humans. And that worked okay in the Iraq War. But then sometimes they swing back towards, no, we want to do that again. And so anyway, that's the rationale. We had generator power, we had radio internet links mediated by this UAV, and desert conditions. I don't know, light desert conditions. It was spring and it was green. So let's have a look. So we went to AeroVironment's field testing area, this ellipse here, just north of the sprawl of the San Fernando Valley. This is all oil company land, and cattle, but it's pretty pristine. And our surgeon stayed in Seattle for the remote operation. And we suited up and packed up rental vehicles and went down there. And this is the site. You can see cows, and we kind of call this desert, but it's pretty green. It was hot, and set up like this on each day. And so the distance between the control station and the remote surgery site varied up to 1 kilometer. But we did a lot of testing locally like this, where there's the remote robot site and the surgeon site kind of within sight of each other. On the days that I was personally there, that's what I saw. I'm sorry about the color of this panorama. I'm not sure what happened. But yeah, so this is our power source. And believe me, that is something that we had to think about in advance and make sure that we had robust power protection for our system. And we kind of worked out all these kind of robustness features of what would normally be a university lab prototype in order to do these things. This is the Puma UAV that we were using, which is supposed to have its own radio, which turned out to be broken on that day. What to do? So back in the day, there was this great chain called Fry's where they had massive electronics warehouses, and you would go there and get with a shopping cart. And I think it's closed down now because of the internet, but we were able to drive to Fry's and actually put in with duct tape a router, a wireless Wi-Fi router, because the plane had a 12-volt power supply, so we could just plug it in there, and that was what we did. And so we also got these long distance directional Wi-Fi antennas from Fry's, and we had a grad student like aiming this at the UAV as it was circling up in the air. And believe it or not, it worked pretty darn well at 1.5 kilometers total distance. And that's because there's no walls, buildings, interference sources. It wasn't that crowded dorm where there's like 50 Wi-Fi networks competing for bandwidth. So it was kind of an ideal use case. And we got this working. So that was cool. And then here's like the surgeon side, that's Dr. Broderick in red, and the remote side that we set up. And here's launching the UAV. They didn't want us any closer than that because it was kind of classified or not, I don't know, protected in some way. But that's how they launch it from a pickup truck by hand. And okay, I talked about that. Again, more pictures with cows, and it was a success. And again, because of all those difficulties scrambling around in the field, we didn't get any peer-reviewed, um, statistically significant results out of it. But we got the confidence that we could kind of field something. And so next year, Dr. Broderick proposed Nemo 12, which is to go underwater and put it into a sort of simulated space station, a kind of a Jacques Cousteau place below about 60 feet underwater, and do otherwise the same thing, but test it in a completely different extreme environment and further test the Raven. So this is a thing they have off the Florida Keys called Nemo Aquarius, and it's used by NASA and NOAA for studying the ocean and nominally simulating long duration space station missions. You could question that because it has gravity, of course, and also the air pressure is about 2 atmospheres in there because it has to keep the water out. And that's very different from less than 1 atmosphere in the space station. And in fact, you can't bring hard drives down there because the pressure deforms the case and wrecks the hard drive. So we knew that in advance. We substituted SSDs, so we didn't have that problem. But we had the problem of getting the Raven down there. And so it had to be taken apart and put into these diving cans and taken down piece by piece, and we had to make a manual with instructions and videos to train the surgeons and astronauts down there how to put it together and boot it and get it running. And that was like a big effort, which improved the usability of the whole thing. And this is what it looks like down there. And that's what the Raven looks like set up down there. And also, it didn't work when they set it up. And my student Mitch Lum, who was in that first picture, he had updated his scuba diving certificate prior to this trip and had to go down and fix it. But he wasn't medically certified for the depth. And so, this is the research advisor's worst nightmare, calling the parents and saying, your son has died in a scuba diving accident on my research project. But I realized that these divers who ran it were Navy SEALs, a team of Navy SEAL divers. So it's about as safe as scuba diving thing as you could imagine with that supervision and expertise. So anyway, but he only had 90 minutes because he wasn't certified for the for the decompression chamber, and at that depth. So, but he finished it he fixed it in 85 minutes, came back up, and the system worked. And Dr. Tom Lenve, who I still collaborate with, was remotely operating it from our department in Seattle. And again, this was one where there were difficulties. There were competing things like supporting a kids' science event in a science museum in Cincinnati that ran long, and then so we didn't have time to do our carefully crafted scientific plan. But the bottom line is then we had taken Raven to another level of productization, if you will, and reliability. And that led to the next project, which is an NSF grant where we collaborated with 7 other schools in the US and funded to build a Raven for them for their research to enable their medical robotics research. And that we built all these electronics boxes and built 7 Ravens, or actually, I think we built about 10. This is Jacob's team, who was then already at, actually, I think he was still at UC Santa Cruz at that point, but building the hardware, our own instruments. And 5 other schools heard about it and said, we want one too, and they gave us contracts. And eventually we spun out a company, Applied Dexterity, to build these, to build more, run off more copies, if you will. And we had a big supply chain at this point. We didn't actually build these boxes. We sent them to an electronics building company. And there's a lot of work to ramp another company up to build your box. But that pays off in making it easier to replicate. And then a grad student dream come true is being asked to go to Hollywood and put your project into a Hollywood movie. And so, oops, that was supposed to play the video. Oh, I know. There's something with screen sharing and playing videos on Zoom. No, it's working this time. So this is a character getting his brain fixed by the Raven. Oh, did you blink? Because this is like 10 seconds. And now we're going to switch the scene to emotional drama and daddy issues and stuff like that with this big stars. And so that was it. So I will show you again the first 10 seconds of this 2-minute clip, because that's the only time you get to see the Raven working. And but it was how many grad students get to go do something like that? They almost got to be in the movie because there was going to be a scene with some technicians operating the robot, but that never got filmed or got cut. But see, there's Harrison Ford. This is Hawkeye King and Lee White. I'm sorry, Lee. Lee White, the 2 students who went down and supported that. Lee is now actually a urologist, finishing he's chief resident urologist at Stanford right now, with obviously robotics training. And so now at this point, I think there's up to 20 now Raven sites where Ravens are set up in universities around the country and world. We're building another one right now for Tsinghua University, actually. So on the software side, this is what opens it up for a lot of researchers. And this was our original design, fully open source, where we have actually originally we added ROS later, of course. ROS didn't even exist. We had Linux kernel, and then we have our control system, which runs at 1,000 hertz in real time with this is a compiler flag for building the Linux kernel with real-time scheduling. And we support different modes now. So there's ROS on top of it, and we have a low-level teleoperation. We call it Internet Teleoperation Protocol, ITP, which runs on UDP. There's if you're not a networking geek, the main thing when you're surfing the internet and probably watching this video, and I'm not sure about watching this video actually, but when you're reading email or surfing the web, you're using the TCP protocol, which is slower but very, very, very reliable. And UDP is much faster than TCP, but it is unreliable. And you could just lose a packet, and that's part of the rules. Okay, so we figured out how to make a robust teleoperation that's robust to um, dropping packets or packets arriving out of sequence, which are things that can happen, but it's much faster. So we could do 1,000 hertz globally over the internet, as you're going to see. We finished a project recently, a great partnership with Johns Hopkins and WPI to develop a common API, because they have developed another research platform which is based on a sort of skeletal Da Vinci hardware that you can obtain under certain circumstances from Intuitive. And it's kind of like trade-in models and things like that, where they strip out all their software and control. But Hopkins and WPI built a controller for that Da Vinci hardware. And so those were sort of two separate research worlds. And we've developed a common API so you can develop code that would run on both platforms. And that means you have, maybe approaching 100 potential collaborating labs if you want to develop to that API. And furthermore, we're farther behind on that objective than I would like, but we also have a simulator that runs this API. So you could develop code with simulation and then spend a couple weeks at any of these labs.
Blake, looks like we lost you on audio.
Is everything okay with audio? Yeah.
Yeah, just
So
came back.
yeah, these are very nice gaming headset, wireless headset, and there's something about giving a lecture for a long time as opposed to sitting in a meeting where the audio drops out once in a while. And I've learned this from my classes, so I could see in your faces that my audio was gone, and so it didn't last too long. Sorry about that. So let's say we want to add haptic feedback to teleoperation. We have delays, distortions, stability. And so we've studied this. What about collaborative haptic teleoperation, like two surgeons pulling on something that they're both grasping? And this is a thing I've studied for a long time. This is sort of like a super high level simplistic overview. If you look at teleoperation of robots at the top level here, thinking about all the degrees of freedom, you may have a leader device. It may be we call this a thumbstick now. It's a little more up to date terminology. Or it could be a leader device that's sort of kinematically different than the follower device. And then we have various kinematic computations to change the coordinate system. Maybe we send some joint commands to a controller, which makes the follower follow. And you could have force sensing in here and send it back. What about that? So there's a bunch of interesting kinematics, but it's very hard to study the stability of that multi-DOF system, which was the initial problem because of these instability. So we abstracted it perhaps too much even to a single degree of freedom to a two-port network, considering efforts, that is forces, and velocities, flows, velocities, at the 2 points where the user is and where the robot is, and making a model which we can abstract from electrical circuit theory. And we had fun, like my student Rick Adams and I had a lot of fun talking to at the time who seemed like a very senior professor from the area of microwave networks. And they used these to study microwave networks. And sure enough, there was a ton of valuable theory there that directly ported over to teleoperation. But one of the models we liked was the hybrid two-port model, and it's really another lecture to go in to give this the coverage it deserves. Uh, and it's good. It tells you you can learn a lot including qualitative and uh, impressions or human performance aspects of the system and stability. The cons are, of course, it's a linear model and it's 1 degree of freedom, and that is a big con. But it sort of was the best we had at the time. So there's many things we could ask about this. We're going to talk about how do we tolerate network delays. And rather than talking about it theoretically, we're going to do some experiments. So this is work from a student, Ganesh Shankaranarayanan, who is down here on the right. And Ganesh made this his PhD topic. And he did a lot of infrastructure where we would find friends around the world with servers, and they would set up a little packet reflector for us. And then we would characterize the link in the real world internet link between our lab and that packet reflector. And that was actually a little complicated for a student because a couple of years in, Ganesh came to me and said, I can't replicate my results from 2 years ago. And I don't get the same answer. And he dug into it, and well, yeah, the UW had upgraded to this new backbone, and it was simply the internet was faster, and that's why the results didn't agree. It was a moving target. So Steve Safaric and he are subjects here. They're doing this collaborative task you see in the lower left, where there's a target. They have to move the cube to track that sphere, which is moving left to right, and they can only push the cube, and it has some friction, viscous friction, so you need to push on it to move it, and you need to collaborate because you can only move it one direction. And sometimes you squeeze it when you're collaborating, and that can be where the force feedback is coupled and you get instability, especially depending on time delay. But we didn't have to have a remote subject. We could just route all their traffic through this packet reflector, either in Vancouver, BC, kind of locally, in the lab itself, really ultra locally in Raleigh, North Carolina, meaning the same country, continent, and then over in Europe, in our friends in Italy, we could route it that way. And here's just packets going by TCP to Italy. And this is 2007, but these are actually, as you're going to see in a minute, these are great numbers for such a long distance, because this is such a short number of hops. One good university and another good university connected by global backbones. There's only a small number of intermediate servers there. So we're going down to like 190 milliseconds for the most common latency, and that's TCP, which is, I'm going to have to double check that. I believe that might be UDP, but at any rate, that's what the network looks like. Of course, it's long-tailed. And so if you're running, here's this case where they're both squeezing the cube, and if the delay is 200 milliseconds, it's a little underdamped, but it is a stable interaction, but only 50 milliseconds more, and it goes unstable with this same experiment. So it's kind of a result there. This is a little different, which is we wanted to show some kind of ubiquity or interconnectivity of leader and follower devices and systems. And we recruited about 9 labs. I'm sorry I don't remember everybody's name here, but there's like TU Munich, UC UC Berkeley, UCLA, um, Imperial College in London, um, a whole bunch, and Hopkins, a whole bunch of kind of globally dispersed. In fact, it was so globally dispersed that and we tried all the combinations, all the connections using a standardized version of our ITP protocol. And Tom Lowe of SRI helped us out with that. I think SRI was in it too. And we developed kind of a standardized HTTP kind of standard so that we could interoperate all these different leader and follower systems. And that was almost successful, almost completely. 28 out of the 30 combinations were successful. And we had to rotate the time because of the global time zones and everything. We did it all in 24 hours. So that was kind of a different issue, which is interoperability. So I'm going to wind up with some very fresh stuff after doing some greatest hits going back embarrassingly long amounts of time. This is a current project with a great collaborator, Steve Sessler, who does electrophysiology cardiology, which means that he works on rhythm disorders, and he does catheter-based interventions into the heart where it turns out counterintuitively there's certain neural nodes in the heart which when they're not working right, the best therapy is to actually destroy them by electrocautery, specifically the sinoatrial node. It sounds so central. How could it even work if you destroy the sinoatrial node? But this is proven and very, very well accepted and tolerated surgery, and it works to stop some rhythm disorders. And he goes in there with a catheter, and you can't see because there's no visual guidance because the heart is full of blood, and he has magnetic tracking and he has force sensing, and he finds the corner that has the SA node in it and he zaps it. But now he's very passionate about remotizing this procedure so that patients in rural areas can get access. And we have some unique or very unusual access issues compared to other states in the United States because we have long distances and mountain ranges between the rural population and most of the providers. So this is a multidisciplinary team looking at this on NSF's Future of Work program. Our follow-up to this was a planning grant. Our follow-up is pending, but we're really trying to prove that concept. And here's an intermediate study. And this is Steve's idea. I'm kicking myself that I didn't think of it myself, but it's a great idea. And what we're doing is simulating the internet traffic of real remote surgery. And we want to look at the rare events, not the typical performance, or not just measure it on one day and generalize, because we know it's good enough on one day. The question is, if you're doing surgery for a year, how often are you going to get disrupted by network properties? We want to see the rare events, the things that happen unusually, because if they happen too often and the surgeon thinks it's not safe or practical, it's pointless. And we assume that the control system will have safe fallbacks for anything, including total loss of the internet. And the FDA would not approve it without that. So there will be safety. But what about efficiency, practicality? And we want to even see rare events. We want to see a hospital where somebody dug up the parking lot and severed the fiber during an operation. We want to catch that. So we have a network that we're expanding of rural hospitals in Washington. They're generally separated from our campus by mountain passes that get very snowy in the winter, for example. And we have this basic setup with the Raspberry Pis. And we're just looking at TCP right now, very small packets of information. The application, the control of these catheters doesn't require 1,000 hertz or anything like what we needed before for haptic feedback. It's much more slow and low bandwidth. So we're only sending 2 packets per second. We're also going to expand this to emulate the protocols of an actual remote prototype that a startup is doing. And then we're running it 5 days a week for 90 minutes plus or minus to simulate actual procedure durations and frequencies. And we know that congestion is potentially an issue. And so we're running another one at 2 o'clock in the morning to see if those stats are different because of less congestion, presumably at 2 o'clock in the morning, which isn't true, actually. So here's our first result with a place called Ocean Beach Hospital out on the coastline. And this is the percent of packets we sent during these simulated operations and the latency. And so how do we break this down? So first of all, we built in the fact that the latency that really matters includes the feedback from what the robot did. So we're giving the robot half a second to respond to whatever command is sent. All this is simulated where there's no robot. It's just that one Raspberry Pi is simulating a surgical robot and the other is simulating a surgeon. And this is from, by the way, we did 54 so far. We've accumulated 54 of these simulated surgeries. So we've learned that, and the orange is the nighttime control and the blue is the morning realistic schedule. And so we've got 4 nines, less than 225 milliseconds. And again, this is sort of a shocking number considering what we got 7 years ago across the Atlantic. It makes me think I mistyped that as TCP when it was really UDP, but I'm going to double check. Follow up with me if you care. So we're, that's pretty good. And actually our worst case is pretty good too. The real latency of the network itself is only this gap above 500 milliseconds. And that's what we're talking about here for 225. This is really a total of 725. And then the other thing is, like, if we look at each operation on its own, what's the worst case latency? Like, did all those bad packets happen during just one operation, or are they spread evenly throughout the 54 operations? And so this is the worst case packet by number of operations. And the takeaway here is 10% of our operations had at least one packet delayed greater than 250 milliseconds. So that's still quite good. But don't forget there's a rare outlier here we saw one night. Okay. Now, nobody's doing nighttime surgery, but if we hope to collect this for like a year. So are we going to see outliers like this during the daytime ever? We want to know. Here's a thing that the traditional literature on internet performance does a lot, which is log-log, or actually they don't usually even plot it log-log, but just cumulative probability density for latency. So along here is latency up to 1 second, and here is the probability that the packet will be less than that latency, the cumulative PDF. So we're getting this 700 plus a little bit. Again, it's really only 225 because of the 500 milliseconds. This amount is just our simulated delay for the robot. The network, the amount due to the network is this amount, and again, we're focusing in on these very rare events, which most people don't look at, but we think they could be disruptive to an operation. So again, these are so many nines because we care about those rare things. And then finally, I'll wrap up. We're trying to get sort of metrics out of all this data, and this is very raw. That's why I put it in courier type here, like I just printed it out, which I did actually. So this is our latest record with 52 surgeries. We define an incident as 700 milliseconds. So basically, I fiddled with that number until I got sort of a reasonable number of incidents, which is not something we're excited about. What we need to do is simulate surgeries and simulate these incidents and see how they affect what a surgeon does, and we certainly are excited about doing that. So we got 263 incidents. Only one surgery had no incidents out of 52. The next metric is how many incidents per hour of surgery are we seeing? So on average, that's 3.3, or 20 minutes per incident, 20 minutes of no incidents per incident. And finally, what's the average delta T between the incidents? Are they coming up in order in bunches or not? And so it's about 12 minutes is the average delta T. So we probably need more like a median delta T or the most likely delta T or something like that. But these are just kind of metrics that came out of my head, and we need to medically validate these metrics and even validate them from the point of view of healthcare economics, which is a person we have on our team, to make sure that this is a practical technology. And then, of course, this is based on today's internet, so it will only get better. So with that, it's possible today. And it's more exciting today because everybody's taking telemedicine more seriously, because a lot of people have started using it during COVID, and a lot of resistance, a lot of conservatism and resistance has been broken down. Not everything, of course. Many interesting issues remain. And I'll say one thing to anticipate a question I sincerely hope you guys are asking, and that is, what about hackers and internet security? And obviously, nobody wants a hacker to take over a robot that's controlling a scalpel inside your abdomen. It's a kind of worst case scenario. And I have two responses. One is we do have one publication on that, which you could look up, and I could with Howard Chiswick, and the second thing is that the issue for us in this community is to just study the security issues which are hyper specific to surgical robotics, because there's a huge, excellent research community securing links like stock trading links and power controller systems and all kinds of mission critical internet links. They're already experts studying them. So figuring out which risks are unique to surgical robotics is a little bit tricky and takes attention. And it's a thing we're planning also in that future of work project. So with that, I'm very excited to take your questions and hear what you have to say. Thank you very much.
Mike, are you returning? Nice talk, Blake, by the way. I'll fill in the void here.
Thanks, Mike.
I've got a bunch of questions. Mike, do you want me to lead the discussion here? What's the procedure?
Yeah, well, we're actually right at 1 o'clock now, so maybe we'll try to keep the Q&A relatively tight. So I see there's two questions in the Q&A, so maybe we can ask those and then maybe have you ask your question or a question or two, Mike, just to keep it relatively timely.
Okay. Actually, the anonymous attendee asks about, basically how bad would it be if you miss a packet or a delayed packet? And actually, I'll just bring a little comment to that. So when I was at Hanson Medical, there was no internet. We were all dealing with internal networking stuff. And we were also confident there'd never be a dropped packet that the system was set up to basically fault and stop working if there was one. And of course, not surprisingly, we had many dropped packets in the middle of procedures, which was a big issue. So I'm kind of curious, along with that question, is I know you haven't really focused on that, but what do you think could be done to mitigate these dropped or lost packets, assuming that they were maybe say less than a second. Do you think that's something that's readily addressable, or I'm curious your thoughts?
Yeah, it's the right question to be asking. It's possible that we're, looking for insects with an electron microscope here, right? And I think for the average typical operation that we've monitored or simulated operation here, I think the performance is excellent and everything will go smooth. And that's why our emphasis is like really actually collecting this data for a year and looking for rare events. Okay. So I think we're showing that it's a non-problem most of the time, but the real answer is dependent on obviously on the control system, on the what it does with these events, these incidents, and again, another assumption I made was that the FDA would never approve it if these things caused a dangerous situation for the patient, right? So that I'm assuming there's an intelligent controller which says if there's a lost packet, maybe it has the way to classify it into a serious situation or one where we can just get the next packet and move on. And it does that reliably. It does that in a validated way safely. And they've proved to the FDA that all that's safe. However, obviously, if a backhoe severs the network connection, you have to fall back to a procedure that may convert it to a manual operation. You have to maybe call in a surgeon from another building to come over and take over, things like that, which are disruptive, and you don't want that to happen, even though it may satisfy the FDA that it's safe enough. So the real thing is we've got to simulate these kind of events, make them more frequent than they are in real life, and have surgeons react to them and then tell us, right? And I think many of these what so-called incidents, even the way our control system is now, which is still a prototype, it's not before the FDA or anything. Even the way it is now, I bet most of them may be noticeable, but the kind of thing where it's like on a Zoom call, if you see a glitch, you just keep going. It may not even rise. People might not even discuss it in the Zoom call, right? It might be a glitch that you just ignore. So I think many of them are that, but we need to identify formally criteria where we decide what really is a serious incident, and classify them like minor annoyance. A, not noticeable at all. B, noticeable but inconsequential. C, minor annoyance. D, requires pausing. C, requires a change in what you're going to do and new personnel or executing a pre-trained procedure, stuff like that. So that's how we'll do it. Is we'll make a simulation and expose the surgeons to those events much more often than they would see in real life to classify them.
Okay. It seems spot on. My own experience is that sometimes safety and procedure flow can fight each other, and being over, not that you wouldn't be safe, but you need to be safe in a way that minimizes the disruption to the procedure.
Another big one though is like, if an event is really rare, then you've got to make sure that the operating room team is adequately trained for that event. Because if they get training once and it happens 18 months later, they're going to not remember it. And so exactly, what training regimen do you need for these fallbacks is, that's a whole nother thing. But we have training experts on our future of work team who will speak to that kind of thing.
I think that's an interesting program with that, very interdisciplinary. I mean, more interdisciplinary than what we usually mean. You get non-engineers, and it's I know Bill Gay has a project, I think, that's a future of work project as well. But I don't think he's here today. He had a baby recently, or is more exactly his wife.
It's a good excuse.
Yeah, yeah. All right, so I think, Mike, correct me if I'm wrong, now it's perhaps time to move into the closed session.
Yeah, maybe we can just ask. There's just one other question in the chat just to
Okay, why don't you
homage.
grab that?
I'll just read it for the sake of time. But this one was actually going back to the desert test. So it was for that field test in the desert. How did you / did you, I guess, test the UAV mediated internet link prior to actually arriving on the field site?
That's the thing. We counted on them. They said it works, and we have it. And when we physically showed up, it's like, oh, sorry, we don't have any boards that work right now. And so it's like, wait a minute, we're not just canceling this thing. And so that's when we said, let's try a Wi-Fi. And that was like literally on the spot improv because of that communication screw. They should have told us, don't come down because none of our radios work. But it was too late. So that's how it really happened, and we got lucky in a way. But it was interesting too.
Your little MacGyver moment there, or at least the team's MacGyver moment.
Yeah, and like I made that picture that showed like half the router sticking out the top of the plane, and that wasn't a photo, but that's actually what it looked like. Okay. And anyway, it worked. So.
That probably was a fun experience for the students to actually, not just give up, but run down to Fry's and figure all that out. I'm sure they remember that fondly.
Yeah, and I do too. That one I did go to. I didn't go to Florida, or I didn't go to the movie set. I'm kicking myself on that one. I really should have made the effort, but who gets to meet Harrison Ford, right? Anyway,
I know you might have been fast friends. Who knows? But now
that's
you'll
right. That's right.
All right. So I think with that, now we need to move to the closed session with Blake. So I kindly ask others to leave the Zoom meeting.